morning. Good morning, everybody. Welcome back to the third day of the CubeSat Developers Workshop. It's great to see everybody here. As always, we are very indebted to our sponsors who help us host this event. Our gold sponsor this year is Blue Canyon Technologies. Our silver sponsors are DHV Technology, Maverick Space Systems, and Apex. So if we could give them a round of applause, I'd appreciate that. All right, thanks again. Some other logistical items. If you signed up for the career fair, there's a schedule for a rotation at the registration desk, so make sure you go up there and figure out where you are within that schedule. If you totally forgot to sign up for the career fair, that's also okay. Go up to the registration desk and talk to Harper once she's done here with the presentation. Let's see, other things. Today's the last day to buy a Hawaiian shirt. You can see the example of the Hawaiian shirts we have up there at the booth. We also have bibs if anyone needs a baby bib. They've been sort of a running joke / staple of the conference. I think we bought probably 500 bibs 23 years ago when when the workshop started, and every year we end up selling like 3 or 4. So if you're interested in a CubeSat bib, they make for a fun little gift. They're up there. Updated schedules online, the CubeSat.dw.org website. I think everyone has been here already, but if you're a presenter, please make sure you're backstage. There's a little more than one presentation prior to your scheduled slot. And those are all my announcements for today. So with that, it is my pleasure to introduce and welcome to the stage Harper Dame and Matthew Fletcher from Cal Poly CubeSat Lab. They're going to be talking about the drag cell project that we're working on there. So please help me welcome them.
Yeah. Hello, everyone. Thank you, Dr. Bilardo, again, for introducing us. As you said, I'm Matthew Fletcher. I'm on the Structures and Mechanisms sub-team here at the Cal Poly CubeSat Laboratory and also co-lead for the drag cell project.
Hi, my name is Harper Dame. I am a part of the Systems Engineering Analysis team at the Cal Poly CubeSat Laboratory and also drag cell co-lead.
Technical difficulties.
Awesome. So let's get into some of the history behind our project. We've had 2 projects in the past, one called CP5, in which we created a drag sail that flew in 2013. It was operational until 2013, and the primary purpose was to investigate the use of a 1 meter squared thin film mechanism. And also we created a project called Spinnaker 3 in collaboration with Purdue University, and we collaborated with them. They created the drag sail payload, and we created the bus. And we flew on Firefly Alpha, which unfortunately never made it to orbit. So now we're currently making our own drag sail. We are working with the Baker Cube Endowment here on campus, and the goal of that project is to create a working prototype by February 2027. That's next year. So that is the main purpose of the project that we're working on right now.
Yeah, so as Harper said, this is a fully internal project at this point. The scope of our funding is only to construct a prototype, but the hope would be that once we construct the prototype, we can secure additional funding to build a full module. This drag sail fits in a 1U form factor and is intended to be integrated onto a 3U host CubeSat. Another goal is to evaluate our ability to design and create a complex mechanical system. And also the hope would be that we can develop this in-house for a lot cheaper than commercial drag cell options, which are around $30,000 for a CubeSat. Additionally, this drag sail design currently is passively deployed, meaning that there's no motors. We'll just have like a burn wire HDRI mechanism. It's also passively stabilized, which I'll get to in a little bit. And then you can see on the screen there, we have a preliminary CAD picture. We had our internal PDR about a few weeks ago, and we're trying to have our external PDR by the end of this quarter.
Some additional things about our module. We're creating an integration unit, so we're not like a full 1U. We're integrating into a 1U form factor. And some of the things to note about this module is that we're employing a jack-in-the-box design in which we have a large spring at the base of our module that will lift the carriage. The carriage holds our board's battery and our boom deployment system. And we're using a 4-spool deployment system, which means that each spool deploys independently from each other. This is different than some of the central 1-spool models that we've been looking at, and this is just as to make it easier for packaging for ourselves.
Yeah, so getting a little bit more into pyramidal stabilization, the most common form of drag sail is what's called a flat sail, so it's just a flat sheet of sail material. This is the most efficient in terms of turning your material into drag area, but a lot of our CubeSats only have passive stabilization, so we wanted to investigate what's called a pyramid sail. So essentially a square pyramid, and because of the geometry, the center of pressure and center of mass are offset. So this creates a restoring torque from the atmospheric drag, which keeps the sail in the flow fields. And the hope would be that we can maximize the average drag area if the pyramid sail is pointing directly in the flow field rather than a flat sail, which might just be tumbling around. And this is a little bit more into the geometry. As you can see, that's a picture of a square pyramid. The two factors that we're trying to control for right now are the boom length and the apex half angle. If the apex half angle is larger, the sail looks more like a flat sail, and if it's smaller, then it looks more like a dart, which means it's more stable, but it has less drag area. So we're actively working to create a simulation to optimize the drag area versus the stability.
As we've been moving into our prototyping phase, we have conducted some material testing with our professor here, Dr. Abercrombie, who has let us do some atomic oxygen testing for some sail materials that we've been looking into. Based on some of her grad students' findings from the past few years, we have ruled out mylar as our material of choice, and we were looking into the difference between CP1 and corin. We tested 1 corin sample and 2 CP1 samples with the reference to a Kapton sample. And the difference between the 2 CP1s to note here is that one of them was folded. We wanted to see if any folds would change the outcome of the degradation of the material. But as you can see, that really didn't matter because the CP1 completely disintegrated in our testing, which then allowed us to make the choice that we're most likely going to go with corin as our material of choice in the future, as it had the least amount of mass loss. Some next steps that we have for our project coming up is that we have our external PDR in May. We also have our manufacturing prototype where we have a summer program that we're going to hopefully be getting most of our manufacturing done with, but then also having a full prototype by February of 2027. We hope to have our testing done within the next fall semester, and then also have our TVAC and deployment tests of winter. So a lot of things on the docket for us. Do you guys have any questions? And thank you.
Yeah. Yeah, exactly. So we haven't fully decided on a release mechanism yet, but as Harper mentioned, we sort of have a jack-in-the-box style deployer. So it kind of looks like a pea pod. The booms and everything is mounted onto a spring plate, and then the spring plate is held into the box with a burn wire. That'd be the idea. And then once the burn wire is released, the entire thing pops open and deploys. Yeah.
For sail deployment, are you guys looking into mechanisms to make sure you get a proper sail deployment before untangling?
Yeah, so one thing that we're looking into is what's called an anti-blossoming mechanism. I'm not sure if you're familiar with that, but if the booms aren't tightly wrapped around the spool and pressure isn't maintained, they can jam up the deployer. That's one thing. Also sail folding, again, making sure that the sail is put in the housing in such a way that it won't interfere or get caught on anything. So those are the two things we're looking at, yeah. Any other questions? Cool. Okay. Thank you guys so much.
Yeah, thank you.
All right, so we are still trying to find our second presenter, so give us a minute. Jesse, if you're sitting out here, please come back. If you're supposed to present, just give us about 1 or 2 minutes and we'll have the next presentation ready. Thank you for your patience.
Next up, we have Jesse Myung and Oliver Yemen from WashU, and they're going to be talking about Scalar, an educational CubeSat mission for magnetic attitude control design.
I'm a little too short for this. Hello, my name's Jesse. We're from WashU Satellite. I'm the chief systems engineer.
And my name's Oliver. I'm the chief mechanical engineer.
Yeah, so I can't see the screen. Sorry, I'm gonna adjust this so that I can see the screen. Can I do this? Screw it, I don't know. Whatever. Yeah, so we're here to show you our systems engineering practices through magnetorquer-based CubeSat development. Before I jump right into our spacecraft design, I'm going to go over why this project is so interesting. So we're trying to do 3D axis control with just magnetorquers, and that is not as trivial as people might think, is because torque is generated when the magnetorquer is perpendicular to the Earth's magnetic field, and if you have 3 magnetorquers, one of them is always going to be aligned with the magnetic field. So we're effectively always going to have one axis of magnetorquer that is uncontrollable. And Scalar is operating under this fundamental constraint. So what's Scalar? Scalar is WashU Satellite's first CubeSat. WashU Satellite's pretty new, and we hope Scalar could give us experience and flight heritage that we need for future spacecraft projects. It's a 1U CubeSat. We have an embedded magnetorquer board that is fully student designed. Yeah, and there are other restrictions that we had to work around besides the technical constraints that I've mentioned earlier. It's that because we wanted to make this happen as quick as possible, we were restricted by lead time and also restricted by budget, which means that we don't have a GPS or sun sensor, star trackers, etc. But that is why Scalar is so interesting, is because we have to work around those constraints and we have to come up with creative ways to do that. So Scalar was designed so that we can give students the experience and we can have flight heritage. Naturally, our mission is pretty simple, is to demonstrate established communication and controls to determine the TRL of club engineering magnetorquers. Our mission objectives is demonstrate WashU Satellite's capability of launching spacecraft and establish effective means and procedure for future satellite projects. And because we happen to have an embedded torquer that is student built, we thought that, let's make this interesting instead of just a beepsat. We can also validate if magnetorquer only control can be achieved in 3D attitude. This is the hardware payload board we have designed, and for the interest of time, we're not going to go into the details of it, but there is the torquer rod that we have wrapped with a tensioner, and those two are on the top, as you can see. And there is a embedded torquer. The reason being is because it's a 1U. We did not have space to shove 3 rods onto our spacecraft, which we were forced to come up with ways to shove a 3rd axis magnetorquer, and decided, hey, let's just have coils around a PCB, and surprisingly it works. I'm gonna briefly go over the control structure. So we're working with a under-actuated space. This shows the nature of the problem we're working with. So you have the Earth's magnetic field, it's the B vector. And like I said, if it's aligned to the Earth's magnetic field, the torquer, if those are aligned, you can't control it at all, you can't generate any torque. So naturally, our control authority lives only on the plane of that normal vector. At any instant, the controller is gonna have 2 degrees of freedom, and the subspace is gonna rotate as the spacecraft orbits. So we came up with 3 big steps to mitigate this problem. Is that 1, we're gonna estimate the current state we have with the sensors we have. We're gonna then get the error between the estimated state and our desired state, and project our desired input onto the controllable subspace. So how are we gonna estimate the full 3D state? Because we don't have any means to do direct attitude measurement, we have to reconstruct these from the sensors we have, which are a gyroscope, an IMU, magnetometers, and 6 photodiodes, one on each side. Using the photodiodes, we plan to either fully reconstruct the sun vector, or we can just use the values that we get from the photodiodes. We're still exploring how we're going to do that. But with a gyroscope, we hope that we can get a reference state, and with those sensors, we're gonna get the error state, which will give us an estimation of where the spacecraft is currently pointing. And this will have to be, of course, reiterated every time step. And now we have an estimation of our attitude. We can now calculate the attitude error. And using the current state, the error of the attitude and the magnetic field, the body frame of the magnetic field, we can calculate the optimal magnetic moment M that would reduce the error that we will have under the current limitations we have. And the point here of the controls logic is that we want this to be able to naturally adapt to the constraints that we are dealing with, which is an underactuated space. Once we do that, we will hopefully get the desired tau, and we will also have to recompute this every time step because the controllable plane will be rotating with the field as it orbits. And the tau we will be getting right out after the controls algorithm will be still in 3D space, which, because our controllable plane is 2D, we'll have to find a way to just project onto a controllable subspace, which that's the animation of how it would look like. So we have the tau, which is our desired pointing tau that will hopefully fix our pointing error. And there's the B field. And of course, there are vector components that align with the B field and will have to be projected onto the control subspace, which gives us tau command. And so with that, we should be able to calculate our magnetic dipole moment that we can directly translate into be able to command our magnetorquers. Okay, this sounds all lovely and great, but there's one caveat. It's that this only works if our assumptions are true. Like, assumptions, we mean that, for example, like, we know the magnetic field B. Okay, but if B is wrong, we're solving the controls problem in the wrong plane. Or another assumption we can make is that the system produces the magnetic moment that we command. Okay, but if the produced M is not what we command, then we're applying the wrong torque. The bottom line here is this controller is only correct if the system matches its assumptions. So how do we make sure our assumptions are verified?
Yeah, so we're in a challenge now where we have limits on our hardware, and controls moves out of a hardware problem, even a software problem, into a problem of team structure to make sure our assumptions are accurate. So the answer to this question, systems engineering. As a brief overview of our team's structure, we follow, sorry, wrong slide. Yeah, if we simplify our assumptions, if we make it easy for people to ask questions and to update designs as they change, we can have more accurate assumptions and make sure that our model is as good as it can be when we're working with limited data. So we use a responsible engineering model where on a project level, we have project manager, systems engineering lead. Then we divide that project into several modules, which each have responsible engineers. And those modules are divided into components, which each have a point of contact. Now, the interfaces between these is really where the big assumptions happen. So we have direct responsibility for those interfaces, with the systems integration lead making sure each module fits into the project and those assumptions stay up to date, and responsible engineers making sure that each component of their module works well together and has up-to-date connections. Notably, we don't divide up our projects by discipline, so chief engineers are somewhere off to the side working with everybody else. So here's an example for Scalar. We have our systems engineering lead and project manager helping divide the project into all of these different modules you see here. We have a systems integration lead working to make sure all of those modules work together. We have let's take an example, responsible engineer for structures. I'm biased being a Mechie. And we have all of these different points of contact for each kind of part of structures. We can divide it up. And the advantage is that every member of our team is responsible for something real. Even if you're a new member, you can be the point of contact for choosing fasteners, the point of contact for doing one type of testing, and you really feel like you own a part, and each of our members has something tangible. When we go to space, they can say, I did that. It's easy to know who to ask questions to. You can always talk to your responsible engineer, or if you are a responsible engineer, you can talk to the systems integration lead. There's no big question of who do I talk to, who do I ask this question to? And there's clear responsibility for the interfaces between parts. So where this comes in helpful is when people have questions. Let's take an example. If we want to know what angular acceleration can the magnetorquers produce. So our point of contact for the ADCS team, he can just talk to his responsible engineer. It's easy to know who to ask questions to. That responsible engineer can go and talk to the structures team and ask, hey, can you find out the moment of inertia? And now we can have both the responsible engineer for payload go and ask the magnetorquer team, how much power do the magnetorquers have? And then the responsible engineer for structures can ask the structure, hey, what's our moment of inertia? You have that CAD model. And we can mark all of those down as testable criteria that we can update as we go on with the project. That way we don't work off of any outdated assumptions. So as far as verification goes, really I'd say our best way to do this is through design reviews. We mark down each of these testable criteria we find when people have questions that their project relies on. And through our 3 steps of design reviews and all the kind of mini steps in between, we'll make sure that whatever assumptions you're making in your design are up to date with the latest data from the other teams. And so through this, we're able to get the up-to-date assumptions we need for 3-axis control, and we can avoid running into the traps where you might be working off outdated data or working off incorrect assumptions. So the future of Scalar, as our colleague showed yesterday, is that we're learning how to build these systems engineering models, how to make good assumptions, and really just how to build a CubeSat. This is our first satellite. And then we have another project, ERIS, which is doing research on gamma ray bursts, developing algorithms, working with optics. And so we hope to combine this 1U project and the research balloon and make our 6U vector, which is a much more advanced craft. So we're really taking this experience with a 1U to try and develop all of the best practices to make sure we can do a very ambitious project in the future. Thank you.
It's a really good first mission, so good luck. Are you planning to calibrate the magnetometer for like the residual dipole of the spacecraft? Are you going to measure and remove that?
Yeah, so there are a couple ways we can go about this. We were originally thinking about just spending a few days or weeks to collect the data that we need so that we can use those to calibrate them. Though a few days ago at the networking event, I was actually told that you don't really need to do that because you can just kind of connect it to a thread and kind of rotate it around, like spin like crazy, and collect and use those data to calibrate those sensors. And I was like, whoa, that's a great idea because we don't have a Helmholtz gauge. But yeah, we are planning to do that.
From your block diagram of sensor integration, it looks like you are using the gyro as a reference for detecting space. That will be drifting, yes?
Correct.
What is your reference frame for amplitudes?
So because the gyro will be drifting, we will have to, hopefully we can collect data on drift. I don't know how accurate that would be. Hopefully we can calibrate our gyro so that we can correct that. Or we could just simply have the software restarted every once in a while to accommodate for that. Does that answer your question?
But each time you do it, you'll be basically slowly tumbling, yes? Because you have no other reference to correct the gyro.
Yeah, that is our limitation. It is very likely that we won't be able to do absolute attitude determination because there is no other way of. Yeah, besides the photodiodes we have, which will probably also have some limitations, it won't be very accurate. But at least the point of this spacecraft project was that we can at least do not regional. What's the word? Local attitude determination. So, yeah.
Yes, let's see. You're using two torques types. One is helical, and then the other one is a flat spiral. And I was just wondering if you have any preliminary data, but you said one seemed to work. It is so compact to use the flat spiral. I was wondering if you had any feeling at this point about the relative effectiveness of this.
Relative effectiveness meaning
The flat one as opposed to the helical one.
the effectiveness of generated dipole moment? Yeah, so we have found out that the dipole moment that is generated by the embedded torquer is significantly smaller than the rods. That is something we still have to explore, but we've actually found some research papers that have attempted having embedded torquers, and they were able to generate enough dipole moment to do things with it. So, but if you're asking about specific studies we have done, we didn't have time for that, and we're planning. Oh, but it's like about order of 10 degrees smaller than. It's pretty tiny.
A magnetometer app for your smartphone, they're better than you think they'd be. I don't know if you're using yours yet.
Oh, we thought we needed an actual magnetometer, but.
To first order, try your cell phone first.
Oh, thank you.
Yeah, so we're running our magnetorquers pretty rarely, partially because they generate a lot of heat. We're planning to experiment pretty shortly in Eclipse mainly. Yeah, they're kind of our experimental payload, and running more than one at a time is kind of a stretch goal of ours. The 3-axis control is a stretch goal. So we'll first establish communications, establish that we can produce a moment with the magnetorquers and have it do what we expect. And then we'll do brief experiments with the actual magnetorquers.
Yeah, are you gonna detumble your spacecraft with your magnet workers? So you'll do that first, I guess?
We're using the flight board from the proofs kit, and they have built-in small magnetorquers that are already flight tested. And so we'll use those to detumble, and then ours are purely an experimental payload. Awesome. Thank you so much.
Thank you.
Our next presenter will be Jeremiah Gale. The title of their presentation is a 3U CubeSat Common Bus Architecture for Increasing Mission Success Through Requirements-Driven Design. Oops.
Okay, good morning, everybody. I'm going to go ahead and walk you through some of the research I've done as a doctoral student at Colorado State University. First, we're seeing a rapid increase in CubeSat launches, but reliability hasn't really improved at the same rate. Data consistently shows that failures tied to integration challenges and compressed schedules. And there's a gap between the growth and the reliability, and it's what motivates a standardized bus approach that I'll present. So at this point, reliability really still remains a limiting factor for some of these CubeSats. And as you can see here, the launch rate has gone from about 2 CubeSats in 2022 to about 400 in 2023. The CubeSats provide a low-cost entry point to LEO operations. And basically, we've seen this increase, but we haven't really seen a flattening of the curve in terms of the reliability issues. Initially, the reliability for CubeSats was about 80% in 2022. It's gradually dropped, but it's plateaued at about 20%, which is relatively high when you compare it to monolithic satellites. Oh, sorry. So the rapid growth in CubeSat deployment has outpaced improvements in systems reliability, and as launch rates increase, systems engineering becomes essential to reduce avoidable failures. As I mentioned, on average, you're seeing about a 20% failure rate in these CubeSats compared to about a 5% on-orbit failure rate over several years for larger satellites. The key difference between the CubeSat and larger spacecraft, according to the research, is the degree of rigor in the systems engineering process, design lifecycle, and integration testing and validation. So the hypothesis here is that CubeSat failures are driven more by rushed programs and weak INT and V&V than technology limitations, and a standardized bus for 3U CubeSats could improve this. Okay, talking about the CubeSat failure contributors. Primary contributors for CubeSat failure, according to the literature that I reviewed, shows about comms being about 20 to 30%, EPS being about 40%. OBC being about 15 to 20%, and the takeaway here is the literature shows that there's a lot of testing that's been omitted during development of the CubeSats that doesn't catch these failures during systems level integration. And the root cause, as I mentioned, are these three systems, the EPS, comms, and OBC. The early failures suggest insufficient testing at the systems level during INT, and schedule and resource constraints drive reduced environmental testing that has been noticed in the literature. It was observed that in the literature and subject matter expert interviews, the primary driver of subsystem issues was compressed schedule. That then in turn forced shortening of the INT and V&V activities to meet schedule. And this points to a lack of full application of systems engineering principles in the design cycle of CubeSats. I'm sorry. So the motivation for a standardized 3U bus. Literature and subject matter experts interviews indicated that the reliability limitations, again, are linked to INT and V&V bus level architectural changes and are not solely responsible. The component quality isn't the sole driver of this. So in other words, it's not hardware failures. It seems to be more systems level, subsystems level, and full CubeSat level integration testing issues. So a 3U common bus would accumulate heritage at the bus level, reduce integration risk, and enable more rigorous, repeatable systems level testing, and would also reduce repeated integration risk by having defined interfaces at the INT and V&V level. The literature that I reviewed indicated that improving reliability requires shifting effort into a standard architecture with disciplined verification and integration rather than, like's done now, is mission-specific tailoring. I'm sorry, I got messed up there. Sorry about that. So the proposed architecture separates the CubeSat into a standardized 3U bus and a mission-specific 3U payload. The bus provides all the core spacecraft function, including power, command, and data handling, communications, and attitude control. The payload interfaces the bus through a well-defined mechanical and electrical interface, supported by interface control documents. And this decouples, reduces integration complexity, enables parallel development, and directly addresses common failure modes identified in CubeSat missions. The literature indicates that improving reliability requires shifting effort into a standardized architecture and using disciplined verification integration rather than relying on the mission-specific tailoring again. And this is the notional 3U common bus architecture. It uses standard boards with the PC104 connectors, standoffs for board-to-board securing, and the EPS system is basically distributed about the center of mass where the ADCS is, and this is just notional at this point, basically coming up with what the architecture for a 3U common bus would look like and basically trying to capture all of the needed subsystems. In order to control how things go together and make sure that the 3U payload would integrate to the 3U bus, there would be a mechanical interface control document that would standardize the payload interface, which would be a 3U payload. It would attach with 14 M2 fasteners, it would go into PEM nuts, and then there would be 2 alignment pins. And this helps establish control and make the payload basically agnostic to what it's mating to as long as it follows an MICD. Next is the electrical ICD, which controls the electrical interfaces. For this round, it uses basically a 51-pin micro-D for data and a 25-pin micro-D for power. And this basically controls the positioning of those connectors relative to where they would need to be for the bus to mate to a payload, 3U payload. And this shows the configuration of the integrated 6U payload for launch and vibe testing. And this shows the on-orbit configuration and also the configuration for thermal vacuum testing. And also this would help with the schedule too. I mean, the baseline schedules here were derived from CubeSat 101 and some literature. The key results, only a fraction of the development is allocated to INT and V&V. NASA guidance from the Systems Engineering Handbook and literature recommends adding margin for critical INT tasks, which often overrun and end up having to be compressed, which reduces, causes testing to be omitted or reduced. And inadequate testing is the primary contributor and could be prevented if we were able to use a common bus architecture. So the 3U common bus development method, using a 3U bus yields savings versus traditional development. Savings and schedule are then reallocated to the V&V and INT activities. The bus is pre-designed, prefabricated, which requires no parallel development. This allows the payload team to focus on the payload design and testing, increasing INT time, and improves probability of mission success. Literature links the success of a mission to thorough INT testing and functional day-in-the-life testing of the spacecraft prior to launch. And also, this allows for more time for TVAC and random vibe, as well as EMI and EMC testing, which are typically abbreviated in the development schedules as needed. And using the literature, I created just a notional development schedule, which shows that you have parallel development of your design, bus fabrication, and then your instrument. And it really, towards the end of it, is what it does is it compresses your functional testing, your INT testing, leading to also environmental testing being compressed. And this causes sometimes omission of testing and shortening of testing, which then leads to issues with the spacecraft on orbit. Moving to the 3U bus development, you're not worrying about building your bus alongside with your payload. You're basically just focusing on your payload, following the MICDs and EICD, and this results in savings that's then reallocated to testing, environmental testing, and functional testing. So again, this shifts the critical path. The 3U common bus critical path shifts to payload design and fabrication and INT. Reduced schedule risk, coupled dependencies, thanks to the current concurrent bus payload development. This enhances INT margin, allowing discovery and fix of any integration issues or development testing issues that are typical. And this, next I went ahead and derived a requirement set based on an index of 6 LEO CubeSats to determine what sort of power and processing they would need. And I then translated the data set into a verifiable 3U CubeSat bus requirements that included structural, thermal, electrical interfaces and INT and V&V. Then I reallocated the requirements to the bus boundaries, enabling decoupled development. I next developed the architecture into a 3U common bus, which I showed earlier, and started from a fixed 3U volume interface, then executed iterative trades, focusing on the subsystem's capability and mass available for a total 6U CubeSat with a 3U bus, common bus. So the implications here for the CubeSat development, it transitions CubeSat development from mission-specific builds to a standardized architecture using a 3U common bus that would then mate to a 3U payload. Decoupling consistent with traditional spacecraft design paradigms. Basically, it helps reduce integration-driven failure by allowing more time to test the subsystems prior to integration and when fully integrated. Eliminates bus payload interface loops to drive late-stage redesign. So if something happens with the payload, it needs a redesign and causes a redesign on the common on the bus. And it also reallocates schedule to INT and V&V, as well as environmental testing. And programmatic, this would also reduce your NRE across missions, since you'd already have a bus that would be built, that you would just then be responsible for the payload and purchasing the bus. And enables a more predictable schedule and reduces delivery risk, as well as also could possibly support rapid response missions in LEO or outside if possible. So that's it. Yeah.
Hey, thanks for this. You know, a common approach we see a lot of the larger manufacturers, not so much in CubeSats. Half your spacecraft is bus. That's a lot of bus. So you alluded to requirements. What do we get for that? How much payload power can you support? And what kind of, are you 3-axis stabilized? What kind of data rates can you support?
I haven't investigated the data rates yet. I've been focusing solely on EPS. So the power, I believe, don't recall right offhand, I think I was looking at 40 watts.
40 watts.
Yeah. And then various configurations I've been exploring are just body mount panels versus the deployable panels. In this configuration, I showed deployable panels.
So this will be 3-axis stable?
Yeah.
Yeah, so, I mean, one of the issues with a standard bus is how do you phase in new technology? Because in reality, you know, what's inside the bus is changing all the time, right? So, have you thought of that?
Yeah, one of the ideas I thought of was getting away from the PC104 standard and going to the Space VPX standard so that you could have plug and play cards for your various systems, your EPS, your OBC, et cetera. So basically adopt the backplane design that you see in traditional spacecraft, where you're having cards that go in, and then you can change those cards out as new capabilities come about. That's something that I'm still working on. I mean, ideally, I've controlled the interfaces, but in terms of the software compatibility, that's still something that I'm investigating. But that is a concern. All right. Anybody else? Okay. Well, thank you.
Next up, we have Candace Doe from the Georgia Institute of Technology talking to us about lessons learned from GPDM integration and testing.
Hi, everyone. Thank you for the introduction. My name is Candace. I'm a master's student at Georgia Tech working in the LightSea Research Group. Yesterday, you heard a little bit about GPDM operations from my colleague, Alan. Today, I'll be focusing more on the integration test and test side of things. So first, I'll be giving a brief overview of our mission, and then I'll be telling you 3 stories from our integration and test campaign and what lessons we've learned for them. So first, what is GPDM? You heard about this from Alan yesterday, but as a brief overview, GPDM stands for Green Propulsion Dual Mode. This is a technology demonstration mission, and we're trying to demonstrate the feasibility of a dual mode propulsion system. This is going to be using the Ascent propellant, which you've heard a little bit about, but it's a non-toxic ionic propellant, and we're hoping to use it for both chemical and electrical propulsion. This here is a brief overview of our ConOps. We'll be doing a series of orbit raising and lowering maneuvers using both propulsion systems. Here's an overview of the institutions involved in this project. We are sponsored by NASA SDMD, and we are project managed, and NASA Marshall Space Flight Center gives us project management, payload integration and test, and also engineering advice. Our payload was designed by MIT and Rubicon Space Systems, and then we at Georgia Tech are doing the bus integration, test, and operations. We are primarily a student team. We have about 6 graduate students and 13 undergraduate students, and we also have 2 professional research engineers joining us. So GPDM is built on the heritage of some other LightSea Research Group missions, 6 of which are shown here. 3 of them have actually flown, including Lunar Flashlight, which I think has been mentioned in a couple other presentations. But GPDM is actually the most complex and most capable mission that we have ever built. It's a combination of components from external vendors like PCT, and also some components that we have designed and built ourselves. You might be interested in our payload here. That's the purple labels. So we have a Sprite module from Rubicon. That's mostly our tank and our chemical thruster. And then we also have 4 electrospray thrusters from MIT. So going a little bit into the AI&T process, we started most of this about a year ago in spring of 2025, starting with subsystem integration, moving into subsystem testing, and then this spring, we're currently working on fully integrating our bus and doing a lot of integrated testing and environmental testing. So the first story I have for you is about our avionics system. This is our avionics stack. It's the heart of our avionics. It's composed of 4 boards. The first one on top is the Xiphos Q7S. That's a COTS flight computer that we procured. But the 3 bottom boards are actually custom designed by our team at Georgia Tech. And because these are custom boards, we have to do a lot of testing to make sure they actually work, first on the ground, and then we want to make sure they work in space. So this is actually a screenshot from one of our test procedures that we use to test like this entire avionics stack. So we actually ended up running this test 5 separate times because as we ran the test, we found a whole bunch of issues within the stack, mostly design issues, but occasionally manufacturing issues. And this eventually led to 10 board revisions across our 3 board designs, right? So that's a lot of work. And this is what that looked like in terms of our schedule. So we started getting our fabricated boards back from the manufacturers and about a couple years ago. And as we did some component level testing, we found a few design changes that needed to be made, and that's the first few revisions. In June of 2025, we ran the first iteration of this test. And we actually expected it to be the first and last iteration because, as you all know, hardware works the very first time you try it. That obviously didn't happen for us, so we did some more revisions, ran this test a few more times. So the big lesson that we took away from this is that design work really isn't done until you fully integrate it and test it and also shift your spacecraft. For us, it was really important that we iterated early and often in the process. Part of why this all took so long is because of the evolution of our team over the past few years. So this is a diagram of what our team looked like in the initial design phase. So you can see each of those little shapes represents approximately 1 person on our team. And we had a pretty even spread in the beginning between our different subsystems. Moving into final design, we had mostly wrapped up the bus design, and we were focusing a little bit more on flight software and operations. And at the beginning of last fall, we were moving pretty fully into AA&T, and so we had a little more people on that and operations. But as you can see here, there's actually no one working specifically on avionics. And that turned out to be a pretty big problem for us because we were doing all of this testing, we were finding all of these design issues, but there was no one dedicated to fixing them. So these squares here actually represent professional research engineers. These are employees of Georgia Tech that we've actually hired to help with our project. And they were supposed to be mostly working on flight software. That's a pretty big hole for us in our team. Our undergrads aren't really software people. And we actually have had to pull these software engineers to work on avionics, and we also had some comms issues pull up. And so because we didn't have a dedicated avionics team, our flight software engineers had to work on avionics, and as you all know, a lot of these CubeSat teams are very personnel constrained. So this ends up being a zero-sum game for us. If we have people working on avionics, we don't have as much work on flight software, and that leads to problems later down the line where we don't have software ready to actually test our system. So some of the lessons learned we took away from this are that we really needed an avionics team until the very end of integrated testing to solve all of these issues that pop up. And also that shuffling this kind of expertise around our most experienced engineers might solve the problems that are most pressing today, but they don't solve the longer-term problems that we might have tomorrow. And all of this ended up impacting our schedule quite a bit. So this is not the only issue that came up, but it's a big part of why we eventually slipped our ship date almost a year out at this point. This diagram kind of shows when we expected to be able to deliver the spacecraft versus when we created the schedule. And so for us, we learned that it was really important to keep reasonable expectations of the time estimated to complete work. And this is not only like the first iteration of your design work and your testing, it also needs to account for the time that you might need to take to do revisions and do additional testing. So the second story I have for you is about our separation switch system. So as you all know, CubeSats usually have separation switches that indicate when the spacecraft has actually separated from the deployer, and then tells the spacecraft to turn on. So in our original design, we had 2 separation switches located on one of our panels, and we actually ended up switching to a system with 4 separation switches. I'm not going to go into all the technical details right now, but as a brief overview of the logic of that decision, this is our initial design with 2 switches. And you can see that there's 2 nominal scenarios. If the spacecraft is still in the deployer, that means the spacecraft is off. And if the spacecraft exits the deployer, the switches are released and the spacecraft turns on. However, these middle two scenarios here are actually single point failures for us. Let's say we've exited the spacecraft, so both switches should be released. But if one of them stays not released, the spacecraft remains off, and that basically is a mission failure for us. And so even though this design satisfies the launch provider requirement, that is, if any single switch is released while this spacecraft is still in the deployer, the spacecraft remains off, this does not help our mission because we have these single point failures. So after a lot of iterations on proposed designs, we eventually decided that the single point failure was too risky for us. So we decided to switch to a new system where we have 4 separation switches. And this helps us satisfy both the launch provider requirement and also avoid these single point failures. So this whole process actually took us 3 months to resolve. And this was a pretty big schedule slip because it happened kind of late into the design over the past year. It took us about 2 months to go through all these proposed designs and pick one, and then it took us about a month to actually implement and test this fix. And so the lesson that we've learned here, this is another contributor to why our schedule has slipped. Hesitancy to revise designs and accept these risks itself is a mission risk, and more importantly, a schedule risk. Part of why it took so long to kind of go back and forth is because we at GT have been working with NASA Marshall, and we actually have fairly different risk cultures at our institutions. So even though we've been working quite closely, Georgia Tech comes from like a R&D culture where we do a lot of technology demonstration missions, we launch small satellites, but NASA Marshall has been doing a lot of human spaceflight missions. They fly a lot of low-risk, high TRL missions. This is kind of what our team structure looks like at the beginning of our project. So we have on the GT side our PI, who talks mainly to our team and also project management over at NASA. So whenever we have a design issue come up or we need to make a decision, the team members on the GT side basically propagate information up to the PI, who then talks to NASA, and then that information has to go all the way back down. So this eventually leads to a big game of telephone between our teams. So sometimes information that starts on our side goes over to Marshall and comes back, might get distorted in some way. So eventually we figured out that the most efficient way to actually do all this cross-communication is to communicate directly to NASA. So at this point in the project, anyone on our team is comfortable picking up the phone and calling anyone on the Marshall side. And so the lesson we've learned here is that these big multi-institution projects, especially ones that we aren't able to walk across the school and talk to NASA Marshall, we need to work together as a single team and not as 2 separate silos. And this has helped us a lot with our decision-making process. We actually got another design fix made in about 2 hours a few weeks ago, so that's a lot faster than 3 months. And so my final story here is about harness routing. And all CubeSats require harnessing, right? On the left here, you can see a top-down view of our spacecraft in the CAD software. On the right, you can see our actual flight unit. So a lot of the components you see on the left, you can't even actually see on the right because they're covered by harnessing. And importantly, here, you see that there's actually no harnessing in our CAD, right? Our initial design didn't really think about how to route all these harnesses and where to put them. And so one harness we actually missed when we did the initial design was the harness that controls our hold-down release mechanism for our solar arrays. So that's that little red box there, that's where the HDRM lives, and we have to route wires from that all the way into the bus to the avionics stack. After some iteration, we eventually decided on this solution where we pass these wires through our very sensitive payload. The blue line there kind of represents where our harness would go, and you can see it passes through the gray rectangle on the right there is our electrospray thruster, which is a very delicate piece of equipment. And so this is a pretty risky operation for us. We wanted to be able to test it before we actually did this operation on the flight unit. And we did that using our very handy 3D model here. This is a life-size model of our spacecraft, entirely 3D printed. And it's been really helpful over the past few months of integration to do these kinds of dry runs and fit checks. This is what that test process looked like. So this is our 3D model, and we basically just practiced passing a wire through the payload and trying to see the best way to do it. And so the lesson we learned here is that CAD is really not a replacement for real-life modeling. For us, doing these kinds of fit checks early and often is really helpful in deciding the best way to go about integration. And this is what that looked like on our flight unit. You can see the little white wire. It might be kind of hard to see from the audience, but they're passing into the bus and going all the way back to our avionics stack. So I want to leave you all with a few questions to think about as you start integrating your spacecraft and maybe thinking about integration. So first of all, you might have a spacecraft designed, and you might even start building it. But how do you make sure it actually will work in space? How do you make sure you test it thoroughly on the ground and make sure that you have the processes, training, and documentation to kind of prove and gain confidence that your spacecraft will work in space? Secondly, do your stakeholders understand how much time and money it will take you to complete certain parts of the project? Right? Especially the stakeholders who might be funding your projects. It's important to have frequent, direct, and honest communication with your stakeholders about how much work you have to do, and help them manage expectations, and help yourself manage expectations as well. And finally, how do you plan to actually integrate each subsystem into the bus, and maybe even more importantly, in what order? Is integrating one subsystem going to stop you from integrating another one? And to help with this, you have the tools, fixtures, and processes that you actually need to practice running integration, practice testing, and finish your AINT phase. All right, that's all I have for you today. Any questions? Yeah.
So out of this process, did you develop some recommendations for future missions, like a single point failure reviewer document or a harness mock-up, things like that?
Yeah, for sure. Some of our lessons that I just pulled from my slides are up here. So as for the single point failures, it sort of depends on what kind of risk tolerance your mission is willing to accept. For us, we're a Class D mission, which actually means we're able to accept pretty high risks, and some single point failure should be tolerated. But yeah, we do recommend basically getting together with your whole team, so in our case, with NASA Marshall and our other stakeholders, and developing a document that explains your risk tolerance at the very beginning of the mission. We've also recommended building these kinds of 3D models early in the design phase, even as you're designing, doing the initial design, and that helps you kind of figure out, when you're holding the model in your hands, can you actually integrate it? Yeah.
Did you compile how many single point of failures you have in your spacecraft?
So I've been working on AINT. That's a question for our systems team. We do have a list of risks on our satellite, and our ConOps will help basically prevent some of those from happening, or figure out what to do if those do actually happen. In the back. Sorry, can you repeat that? Okay, so there's not one single issue. So I listed a few of these. Sorry, I have a lot of slides. So the one that I showed on the screen here was actually a misalignment in the stacking connectors between two of our boards. Let's see here. And that ended up being a pretty simple board revision. So you can see on the right here, that little red box, those two connectors are actually misaligned. And so they do snap together, but that causes the connector to kind of lift off of the board. And so this was a pretty simple change. We basically redesigned the board, shifted that connector over like a millimeter or so, and that worked after that. Some of these other ones also involves just like swapping components out. Any other questions? Yeah. Right, so this change did not happen in a day. It took place over the course of a few months. And some of it was honestly developing personal relationships with some of the folks on the NASA side. Being able to pick up the phone and call them and trusting them to give you advice and not like get mad at you for finding an issue or something like that. Yeah, and we were very lucky that the folks on the NASA side were very receptive to this sort of thing. Does that answer your question? Cool. Anything else? All right, thank you all.
Our next speaker is Kirsten Ebersol from the University of Delaware. Their presentation is titled the Delaware Atmospheric Plasma Probe Experiment. So give it up for Kirsten.
Good morning, everyone. Thank you all for taking the time to be here today. It's so important that we continue to come to these types of events. So thank you. Without further ado, this is the Delaware Atmospheric Plasma Probe Experiment, also known as Dapper. So, as I just mentioned, this is a plasma-focused experiment, so I figured I'd start off by kind of talking about what plasma is exactly and what part of the atmosphere we're trying to study. So, we are primarily looking at the F2 layer of the ionosphere. Depending on the time of day, when you're looking at the ionosphere, you have some different structures. So at night, you only have the E and the F layer, but during the day, you actually have the E, D, and F1 and F2 layers of the ionosphere. And so there's a lot of dynamic change going on here, and we don't really understand it well. So being able to map the ionosphere in some way would help to develop a fundamental understanding of the ionosphere. The ionization that's going on in this plasma primarily depends on the solar radiation, which is why you get these different layers depending on the time of day. It's very important to understand the ionosphere. I think a lot of people don't realize how impactful it is. There are all kinds of technology that are impacted by the ionosphere. So, for example, sorry, I'm having a hard time reading the screen. So, one thing my PI likes to talk about is autonomous tractors. And so, these autonomous tractors depend on GPS signals. Back in 2024, we had a geomagnetic storm that occurred due to some solar flares that were going on in space. And so when this happened, these tractors couldn't actually get a good lock on the GPS that they were relying on. And so these tractors that are meant to go in straight lines up and down the fields were getting these wavy paths that were going on, as you can see up in the picture here. And so I know most of us probably aren't operating tractors, but you can kind of get an idea of what the ionosphere impacts. Additionally, you have shortwave broadcasting and emergency and disaster communications. All right, so this is Dapper. Up here you can see our stowed and deployed configurations. Main difference being the antennas and the probes are sticking out in the deployed configuration. But this is a 3U CubeSat, as you can see. And it was approved by NASA CSLI in 2024. Hopefully, we'll still be launching with CSLI. Knock on wood. But we would most likely be through an ISS deployment on some sort of a restock mission. This would put us at about 420 kilometer altitude nominally and at a circular orbit. Because it's a circular orbit, we'll better be able to map the electron density in the F2 layer of the ionosphere. Additionally, we hope to compare the Langmuir probe setups. So we'll have single and double probe configurations, and we'll be switching between those two methods. And we'll be comparing the efficacy of both to see which is better at determining electron density in the ionosphere. It's also Delaware's first orbital spacecraft, fun fact. All right, so Langmuir probes are our main instrument, as I mentioned before. The idea is that you apply a voltage to these metal rods, and then from there you can measure the current that's traveling through the plasma, and by getting these current readings, you can infer the electron density and the temperature that's going on in the ionosphere at that point. So we'll pair that with time data as well, and then we can begin to map the electron density in the ionosphere over time. We're very lucky to have a lot of heritage. So as I mentioned, this is our first CubeSat mission and our first orbital spacecraft in Delaware. However, we've utilized a lot of the RockSat programs. So if you're not familiar with those are sounding rocket missions. We've done both RockSat-C, RockSat-X, and now just RockSat. But we've been able to test primarily our Langmuir probes, but also some software, some hardware. As you can see, we have many missions. We're currently on our 6th UDIP mission, which stands for University of Delaware Ionospheric Probe Experiment. And we'll be beginning our 7th this summer. All right, as my colleagues talked about on Tuesday, we'll have a burn wire mechanism. And because they talked about it, I won't go into too much depth. But basically speaking, we'll have a 38 ohm resistor to burn a 20-pound fishing line. And that will allow us to basically spring out our booms. They have done extensive testing. And I would say that the most current testing we'll be working on is TVAC testing. In addition to our burn wire mechanism, we have a deployment board. So that houses the resistor that will burn our wire. It also will host a magnetometer, which we can use to help confirm our deployment. So we'll look for a significant change in the magnetometer reading, then we'll have some idea that the probe is probably sticking out at that point. As a second method of deployment confirmation, we'll have cameras, two, each one pointed at our Langmuir probes. And while they won't be taking pictures of the Earth, they will be taking pictures to make sure that our probes have deployed. All right, so this is our flight computer. It hosts an Arduino Portenta H7 Lite, and it also is responsible for our cameras. So they're just making sure that it's running and taking those photos and then sending them back down to us at our ground station. Luckily, as I was talking about with our heritage, this actually flew with UDIP 4, a previous version, but general idea, flew on UDIP 4. And it was also a master's thesis project by one of our team members who has since moved on to Berkeley's SSL. So shout out Rania. But we've been through many iterations, many versions of the flight computer, currently on version 3.5. And that 0.5 is because we were having issues with the data transfer of our cameras. Hopefully it's fixed now, though. All right, so our science board, I like to say it's responsible for the magic that goes into our probes. As a mechanical engineer, the probes are somewhat magical to me. But the idea is that our science board applies a voltage to these probes, And then it's able to measure the current passing through the probes to our plasma. So in the single probe configuration, it will send it through one probe at a time. And during double probe configuration, it will send the voltage through both probes. This is an analog board, and it's required due to the low currents that are being measured. We're in the microamp region, so very small ampage. Additionally, we hope to compare the effectiveness of both methods. We're lucky to have a ground station. This is called Mount Cuba Observatory. It's about a half hour from us. So currently, right now, we're working on how to communicate with our ground station from our home lab, and then also communicate with Dapper from there, so that we're not constantly at our ground station a half hour away from campus. It's completely student operated and student maintained. So like I said, we're always out there, but it's about a half hour from us, so it's a little far. Operates at about 915 megahertz. However, it's under some upgrades right now. The facility itself is undergoing some plumbing issues, and we're hoping to possibly upgrade our radio board soon. So we'll see. Some other commercial off-the-shelf components that we have include the EnduroSat solar panels, the ClydeSpace Starbuck Nano, and the Optium's battery, as well as the EnduroSat UHF antennas, the ArduCam Megas, and the Narrowbay UHF radio board. Moving forward, we'll have the UDIP-7 RockSat mission, which will continue to test some of our instruments, primarily the Langmuir probe. And then we have our CDR coming up, actually about a week after this conference. And then we also have our PPRR in hopefully fall of this year. Additionally, as we finalize our designs, we're hoping to do a lot of integrated testing and start assembly very soon. All right, that's all I have for today. I'd love to open the floor to questions. Oh, yeah.
Really interesting science. You're doing science on a CubeSat mission. That's great. In an area that not a lot of people are familiar with, and you're trying to measure very small currents. Do you have the ability to test this on the ground? Do you have a plasma chamber or something you can go into and see if it really works?
So the question was, how are we testing the plasma readings or the current readings here on Earth without any sort of plasma? We do not have a plasma chamber. Ideally, we're mainly making sure that it is running correctly. We have also been able to test these same Langmuir probes on the UDIP missions, which also reach the ionosphere. They're just much shorter missions, which is why we can't map the ionosphere using the sounding rockets. Yeah. Yes, so our primary mode of confirmation will be the magnetometer on the deployment board. So there will be a magnetometer behind each probe, and when they deploy, we should theoretically receive a different magnetometer reading, and that will be another way to confirm deployment. Yeah, back there. So the question had to do with our budget, correct? And how long-term our funding is. So yes, our PI manages our budget entirely. We're primarily funded through the Delaware Space Grant, which continues to give us funding of some sort. We are currently reaching the end of our extended grant, So we would most likely need to request another grant after Dapper launches. But then we also receive funding for the UDIP missions with the RockSat team. Yeah, up there. Yeah, so the question was regarding our measurements through orbit, through the different layers, and at different times of day. So because it's a primarily circular orbit, we plan to stay in mostly the F2 layer, or just the F layer, depending on the time of day. But we're also taking time readings, so we'll have a clock on board our flight camera, and we have accounted for the drift that occurs with that. It's very minuscule. So we'll be pairing our time readings with the current and temperature readings that we're getting, and from there we can kind of infer where we are. We do not. That might be an interesting thing to consider, though. Okay. Thank you very much. Have a great day.
Thank you. Enjoyed learning more about Dapper. That concludes our final session here at CDW. Thank you very much for coming out. Thank you for all the sponsors who helped make this possible. We have dates set aside for next year. Hopefully we'll be able to see you again. So it's April 13th to 15th, 2027 next year. That is hopefully pending deconfliction with the Space Symposium as well. But that's our current plan. If you register to participate up in the career fair, that's going to start at 11:45 in the lobby. If you're not sure about what the time rotation for that is, check in at the registration desk upstairs. And again, thank you for coming. Really appreciate it. Enjoyed meeting and chatting with all of you, and I hope to see you next year.